Every year, the United States builds over 40,000 kilometers of new roads, and nearly 30% of them are made with concrete, designed to last 40 to 50 years and carry loads of several dozen tons. But behind these seemingly ordinary roads lies a surprising world of advanced engineering. Road beds are compacted as firmly as skyscraper foundations, steel reinforcements are placed with centimeter-level precision, and massive concrete paving machines, stretching dozens of meters long, operate like industrial robots right on the construction site. Ever wondered how American engineers turn a pile of raw materials into some of the most durable concrete roads on Earth? Let Mandarin Tech show you how. When people think of roads, most immediately picture asphalt. But in the United States, concrete roads are also a common choice. In fact, over 30% of the federal highway system is built using cement concrete. While concrete may not offer the same smooth driving feel as asphalt, it's often preferred for major highways due to its many technical advantages. Concrete roads have a lifespan of up to 34 years, twice that of asphalt roads. Second, they are less prone to sinking or warping from heat, making them ideal for routes with heavy truck traffic. Concrete also helps speed up construction time, especially when paired with continuous paving machines. With this technology, crews can complete up to 3 to 5 kilometers of concrete roadway in a single day, significantly reducing project timelines. The first step in building a concrete road is checking the route, the ground conditions. After choosing where the road will go, engineers look at the terrain to understand the strength and quality of the soil and rock underneath. They figure out how much dirt needs to be removed or added, and think about how the work might affect traffic and the environment. This helps them decide the best way to build the road, like how many lanes it should have or how long the road will be. Once the plan is approved, the construction team gets to work, clearing the area, removing plants, and raising or lowering the roadbed to match the land. The soil foundation has to be compacted so it's strong enough to support the concrete pavement and the vehicles that will use it. A grader is used to level the top layer of soil. At the same time, underground systems like electricity, water, and drainage are also installed. Roads without sidewalks may have drainage ditches built along both sides. Once all the underground utilities are finished, the contractor begins building the road base, the middle layer that helps transfer the weight from the concrete surface down to the soil. First, a layer of large crushed stone is spread evenly across the ground, then compacted using a vibratory roller or steel wheel roller to make sure it's firm and uniform. Depending on the terrain, expected truck traffic, and weather conditions, this stone layer may be built in multiple levels, a thicker bottom layer and a finer top layer to create a stable surface for the concrete. Heavy rollers continuously move back and forth across the entire road bed, compacting the soil and stone to increase load-bearing strength and reduce the risk of future settling or cracking. Normally, this compaction stage can take anywhere from 2 to 4 days, depending on the length of the road and the moisture level of the soil. During this process, a water truck drives ahead of the roller to keep the ground at the ideal moisture level, helping the soil particles bind together and reach proper density. The entire process is closely monitored by field technicians using compaction gauges, vibration sensors, and laser surveying equipment to ensure all measurements stay within the allowed tolerances. After the roadbed has been fully reinforced and compacted, the crew moves on to the most important stage, pouring the concrete surface. All of the concrete is supplied by an industrial batching plant, where the materials are measured and mixed with near-perfect accuracy. The process starts with transporting raw aggregates to the plant and loading them into inline storage silos using wheel loaders or conveyor belts. Each type of material, like crushed stone, fine sand, or gravel, is stored separately in individual compartments made of steel or concrete, depending on the customer's setup. These silos are designed to hold 4 or more types of aggregates, making it easier to mix the right proportions later on. Once the aggregates are stored, each type is weighed using a calibratable belt scale system. This equipment measures the exact amount needed for each concrete batch based on preset mix designs. After weighing is complete, the aggregates are sent to a feeder bucket for the next step in the process. Next, the measured aggregates are dropped into a large capacity feeder bucket. Its special design ensures all material is fully discharged, leaving no leftover residue. Next comes water. It's sourced either from the local supply network or on-site storage tanks, then fed into an independent water weighing system. The required amount is measured precisely and released into the mixer via free fall or through a high-pressure pump and spray nozzles, depending on the plant's configuration. In parallel, chemical admixtures such as superplasticizers or accelerators are also added. These are measured separately using a dedicated dosing system to ensure accuracy and no cross-contamination. Once all ingredients are ready, they are loaded into a high-performance concrete mixer. Depending on the project's needs, the plant can use either a pan mixer or a twin-shaft mixer. Both systems provide fast and efficient mixing, producing a well-blended, high-quality concrete mixture within a short cycle time. Finally, the finished concrete is discharged directly into the ready-mix trucks waiting below, ready to head to the construction site for paving. These trucks need to move quickly because, on average, concrete can only be used for about 1 to 2 hours before it begins to harden. During transport, the mixing drum keeps rotating continuously to prevent the concrete from separating or setting too early. Once on site, the truck approaches the concrete paving machine, ready to discharge the mix into the system. When the truck arrives, concrete is discharged into the receiving hopper of the concrete paver using a chute or a powered conveyor. This step requires tight coordination between the truck driver and the paver operator to ensure that concrete is supplied evenly and continuously, preventing gaps or delays in the paving process. For long-distance paving or highway work, a line of mixer trucks is scheduled in rotation, so there's always one unloading, one arriving, and others queued up. In modern setups, the conveyor connects directly between the truck and the paver, which helps speed up the feeding process and reduce material loss during transfer. As soon as the concrete is fed in, the slipform paver automatically spreads it evenly across the prepared subgrade, following the exact width, thickness, and elevation specified in the design. There's no need for any follow-up rolling or manual leveling. The machine is fully equipped with vibrating pans and a slipform mold that compact and shape the concrete while it's still wet. Inside the machine, an auger or spreader continuously moves the mix forward, distributing it uniformly before it enters the forming mold. Built-in laser sensors, GPS systems, or 3D guidance tech ensure that the final surface stays flat, level, and aligned. During paving, the machine automatically feeds round steel dowel bars from its storage tray and places them in the middle of the fresh concrete. These bars are set across the width of the road, right at mid-depth, to help transfer the load between adjacent concrete slabs and reduce cracking at the joints. Thanks to the built-in dowel insertion system, this step is done fully automatically, without stopping the machine or interrupting the paving process. Even on long, winding road sections, thanks to its continuous slip movement, the paver leaves no cold joints between loads, creating a seamless, monolithic slab that's stronger and more durable. Machines like these typically cost anywhere from $120,000 to over $300,000, depending on their size, configuration, and level of automation. With high output and extreme precision, slipform pavers are now the gold standard for building large-scale concrete roads worldwide. Immediately after finishing, a liquid curing compound is sprayed over the entire concrete surface. This coating helps retain moisture, preventing rapid drying and allowing the concrete to gain strength gradually. A few hours later, once the concrete begins to harden, workers use special saws to create expansion joints at regular intervals. These joints allow the concrete to expand and contract with temperature changes without cracking, preserving the surface over time. A few hours after the joints are cut, workers clean out all the dust and debris inside the gaps, then pump in a layer of special sealant, usually polyurethane, silicone, or bitumen. This sealant keeps water, dirt, and other materials from getting into the joints. Without it, water could seep down through the cracks and cause peeling, cracking, or even damage the base layer underneath. After the entire concrete pouring and initial curing process is complete, workers begin by marking the traffic lanes with yellow paint and placing no entry signs to block vehicle access for at least 7 days, allowing the concrete to fully harden and reach its design strength. During this period, The roadway is strictly off-limits to any traffic or heavy loads that could damage the surface. Finally, site engineers conduct a full inspection and final quality check, including compressive strength tests, surface flatness assessments, and uniformity evaluations, before officially opening the road to use. While concrete paving machines are common in the U.S., in many developing countries like Peru, road construction still relies heavily on manual labor. Instead of using a slipform paver, workers pour concrete directly from mixer trucks using metal chutes, then spread it manually using shovels, rakes, and long screed boards. The process requires dozens of workers coordinating in real time, as any delay can cause the concrete to start setting before it's properly leveled. After the initial spread, some workers use handheld vibrators to compact the concrete, removing air pockets and improving density. Others follow closely behind to trowel, smooth, and texture the surface using steel floats or hand rollers. Every step is done by hand, relying on the worker's experience and on-site judgment. Without guided systems or leveling sensors, it's difficult to achieve high precision in elevation or flatness, especially over long distances. Still, this method remains common in remote or low-budget areas where access to modern machinery is limited. It highlights a clear contrast between high-tech automation and traditional labor-intensive methods in global infrastructure development. Next, follow me to China, a country known for having some of the most advanced infrastructure in Asia, to see how they build roads. And what makes this even more impressive is that the road we're about to see is being constructed right in the middle of the hottest desert in the world, the Taklamakan Desert. The first step to building in the desert is to create a flat surface and fix the sand to get a foundation to build on. Hundreds of bulldozers were deployed to flatten the dunes, cutting down the high ridges and redistributing the sand into lower areas. The goal was to create a smooth, balanced surface strong enough to support construction machinery without the risk of collapse. Each section was carefully scraped and leveled under strict supervision, with surveyors checking elevation and slope to ensure uniformity across miles of open desert. Conveyor systems push the excess sand away from the work zone, while compactors gently press the top layer to form a firm and workable foundation. After the bulldozers had leveled the dunes, the sand still needed to be stabilized. Engineers discovered that injecting water into the loose surface helped bind the grains together, creating a denser and more cohesive layer. Using long sprinkler arms and underground pipes, they sprayed controlled amounts of groundwater across the site, allowing moisture to penetrate several inches deep. Once the sand reached the right level of dampness, heavy rollers moved in, compacting the surface to remove air pockets and lock the particles in place. The constant rumble of steel drums echoed across the desert as each pass of the roller turned soft, shifting sand into a firm, uniform base. By the time the surface dried under the desert sun, it had hardened enough to carry the weight of cranes, mixers, and supply trucks. A solid foundation built from nothing but sand and water. After the surface had been compacted, workers began spreading a base layer of soil over the stabilized sand. Dump trucks poured out loads of reddish earth, which bulldozers then pushed and leveled across the area. This layer added weight to the sand below, strengthening the surface and keeping it from shifting under heat or vibration. Each section was evenly spread and compacted, forming a dense, stable base strong enough to support the first stages of construction in the desert. At the edge of the desert, portable asphalt plants roared to life, heating stone, sand, and polymer-modified bitumen to nearly 170 degrees Celsius. From these stations, insulated tankers delivered the hot mix non-stop to the paving machines waiting on site. Each paver spread the glowing asphalt in layers about 6 centimeters thick, while steel rollers followed close behind, compacting it before it could cool. This process was repeated in a tight choreography, paver, roller, finisher, moving forward like a synchronized machine. The first passes used heavy steel drums for compression. The final ones switched to rubber tire rollers, which kneaded the surface to seal tiny air gaps and create a smoother texture. Thermal sensors on each paver tracked the surface temperature in real time. If the asphalt dropped below 140 degrees Celsius, rolling stopped immediately. Otherwise, cracks could form once it cooled. Supervisors checked flatness with laser beams, allowing no more than 3 millimeters of deviation per meter. As the desert wind cooled the surface, the asphalt hardened into a flawless black sheet, tough enough to withstand temperature swings from -25 to +70 degrees Celsius. To finish, workers sprayed a protective seal coat, giving the surface its signature deep shine and locking out moisture. By dusk, the newly paved highway gleamed under the sinking sun, a dark, mirror-like ribbon stretching across the golden sea of sand. What had once been an empty wasteland now reflected the light of progress, born from heat, steel, and human endurance. So after 4 grueling years of construction, the 4-lane highway cutting across China's largest desert finally stood complete, a powerful testament to human determination and technological mastery in the heart of the Sea of Death. This project not only connected the far ends of Xinjiang, but also showcased an engineering achievement so remarkable that even American engineers couldn't help but be impressed. That brings us to the end of today's video. You've just explored how concrete roads are built, from the US to China. All information was carefully gathered from various reliable sources, but if you spot anything inaccurate, feel free to leave a comment, and we'll see you in the next video.